Hi, and welcome to 2.2 Speed and Velocity. In this lesson, students will be able to describe the difference between and calculate speed and velocity. So, speed versus velocity. Speed is the rate at which an object is moving. It's a scalar quantity, and you can use this equation. S is equal to d over t. These stand for speed is equal to the distance divided by the time. It's a rate, so that's why you have the division there. How much distance do you travel per second? Similarly, but slightly different, velocity is the rate at which an object is moving and the direction that it's traveling in. Since you're including the direction, that makes it a vector quantity. And you can remember that velocity is a vector because they both start with v. And the equation looks even similar. V is equal to d over t. But what do you think the d stands for? Is it still going to be distance like it was before? Or should we use a different d? The velocity is equal to the displacement divided by the time. See, distance is a scalar, speed is a scalar, displacement is a vector, velocity is a vector. So the scalars with the scalars and the vectors with the vectors. This equation can be found on your reference table. Pull out your reference table, take a look for it. Where is it? It's on the back page. All right, page 6. They only give you V is equal to D over T. And you could even look up, see all these letters? This is really the first equation that we're learning. So just so you know, all the letters are listed alphabetically over here. Here's velocity or speed. And the V bar is actually given over here as average velocity or average speed. Now they don't give you the S equals D over T equation. That's the first example of the reference table being as efficient as it possibly can with its space. The people who made this were basically like, if you know what speed is, you know what velocity is, you should be familiar with this equation and not have to also put in S equals D over T and specify the difference. So that's why only one of the equations is in there. Now for the average velocity thing, later on we're going to do final and initial velocity, and then we'll see how that ties into an average velocity and how they're different. But for now, we're not changing our velocity at all, so the average velocity is the velocity. A helpful hint, you might have seen this when you're doing your density formulas in other science classes. So D is equal to M over V, you know, the whole broken heart thing. It looks like a broken heart. But you could also do this triangle method as well for that. So basically the way this works is if you're looking for velocity, you do distance divided by time. So it would look like this. The equation looks like this. Now, if you're looking for, let's say, time, this little triangle tells you, okay, time is equal to displacement divided by velocity. And that is just, that is just the equation that we have reworked so that it's solved for time. You could do the same thing for displacement. If you're looking for the displacement, that means it's velocity times time. They're next to each other. And this is also a valid equation. But it all comes back to the one that they give you in the reference table. So typically I start with this one because that's what's given to you. So I like to use the reference table as a jumping off point when I do the problems, just because I know you have that resource. But if you feel like doing any of those shortcuts or anything like that, that's fine too, as long as they're valid equations. So D versus T graphs look something like this. In the do now, we did a little bit of exploration of what a distance versus time graph might look like. This is important to remember. In a distance versus time graph, the slope represents the speed. And in a displacement versus time graph, the slope represents the velocity. So this is what a position or displacement versus time graph might look like. So study this, try to interpret what's going on. Let's say this is showing the position of a car over a certain period of time, 10 seconds. Think about the motion of the car. If you were visualizing that car's motion, what would it look like? All right, so for the slope, it's y2 minus y1 over x2 minus x1. So during the first 5 seconds, the car is moving. It does have a slope, which means that it does have a velocity. So it would be 25 divided by 5. It's moving at 5 meters every second. During the second half of its trip, the slope is 0. y2 minus y1, 25 minus 25 is 0, and it's stationary for those 5 seconds. So it's moving at a constant velocity, and then it's stationary. So just by interpreting these graphs, we should get an idea of what the movement of these cars or whatever the object looks like. All right, and you could see if you plug in instead of y2, this y values are the position, and the x values are the time, and that's how we actually get our equation d over t is equal to the speed or the velocity. And a displacement time graph might look like that. The slope m is equal to change in y over change in x. The y values, again, are displacement. The x values are time, which gives you an equation that looks like that. So that's your velocity. That's just proving that the slope is the velocity. Don't forget, in a displacement versus time graph, the slope is the velocity. And the same with if it's a distance versus time graph, it's the speed. Okay, so let's do an example. Now, when we're doing these word problems, I like to do something that's called the guess method. The guess method looks like this. And if you're taking a test in the class and you're having trouble, you'll be like, Mr. Nangle, I really don't know what to do. I'm going to appear to be very mean. I'm going to walk over to you and I'm going to look you right in the eyes and I'm going to tell you, you better guess on the question that you don't understand. And it seems like I'm being mean, but really I'm giving you a hint because this is an acronym. I want you to write down the given information. Then I want you to write down the unknown information. What are you looking for? Then I want you to find an equation. In physics, finding which equation you're supposed to use on that big long reference table can sometimes be the hardest part. By writing the given and unknown information down and organizing yourself, you'll have a better chance of finding the appropriate equation rather than just trying to read this big long word problem. So we're just getting ourselves organized. Once you have the equation, I want you to substitute with units. Units. Okay, so to get full credit on the Regents exam, not only does the solution need to have units, you need to rewrite all the units from the problem to get the point for units. Okay, I'll show you an example. I'm going to grade that way on tests and quizzes too. It seems really mean, and I think it is too, but that's how the Regents exam does it, so I want to make sure that we're following that protocol. Now, the last S you might have guessed is to solve. And again, in your answer, it's very important to write your units as well. So let's give this a shot. The question says you're driving in your car with a speed of 25 meters per second, which is about 55 miles per hour. So that's the speed limit on 287. So the speed is equal to 25 meters per second. Okay. Now, I mentioned substitute with the units down here. If you write your units while you're writing down your given information, that counts as well. You don't have to write them in the equation that we'll get to later. This counts too. All right. Now it says you look down at your cell phone for just 2 seconds. That's illegal. Don't do that. Okay. Don't look at your cell phone while you're driving basically a death machine. These cars and trucks, you're driving a huge hunk of metal at crazy speeds. But you're just sitting in your car and everything's fine, just like you sit on your couch. So you look at your phone. But if you look outside your windows, you're moving really fast. So anyway, the time that you look down for is 2 seconds. How far did you travel in those 2 seconds? So they're looking for the distance that you traveled. So these were our given information. This is the unknown information. What are they looking for? That's the unknown. Now we need to find an equation. And it's always going to seem obvious because I just introduced the equation. So yeah, of course, that's the equation we're going to use. S is equal to D over T. But as we get more and more equations, and you're just doing the problem on your own, it might not become as immediately, you might not know right away which equation to use. So we're going to substitute. So that's the equation. Then we're going to substitute in the values. So S is 25. Then D is what we're looking for, and we're going to plug in a 2 over here. And then you can solve. Now, could you write the equation, then solve, and then plug in? That is a totally valid way to do it too. And some physics people like to do it that way because when you're solving, you just have nice letters there. And if these numbers are really big or really small with, scientific notation, it could get messy when you're plugging in numbers. For now, it's not that bad, but like it's kind of a pro tip to solve for your missing variable first and then plug in the numbers and then do the math. But anyway, you wind up doing the same thing. We're going to cross multiply and we get D is equal to 50 meters. So what does that mean? You're traveling a half a football field at 55 miles per hour and you're not even looking at where you're going. So during that half football field or 50-meter distance, anything could have happened. A car might start moving into your lane. Maybe a ball is bouncing across the street and a kid is going to come. So don't look at your cell phone is the point, okay? And also the point is to write your units here and here to get full credit. You need to write your units when you're substituting in the values. And I'm going to point to this video in the future if I take off points and somebody's like, you never told us that. I wrote it in the answer. Yeah, you got to write it. I just said it for the substituting values as well. Okay. Okay, so example 2 can be a little bit tricky. It says car A is moving in a straight line at a constant speed of 20 meters per second. So we'll write that down. VA is equal to 20. Make sure you get points for units. Car A is initially 200 meters behind car B. Car B is moving in the same straight line, but it's moving at 15 meters per second. How far must car A travel from this initial position before it catches up with car B? So for this problem, there's two different ways to do it. I'm going to do one way, and then we'll talk about relative velocity, and I'll show you another way to do this. And if you think of a different way to do it, that's totally fine too. This is kind of a tricky question that requires some critical thinking. So I like writing the distance that A is traveling is equal to the distance that B goes plus another 200 because it starts 200 meters behind car B. So they're both traveling. It travels as far as car B does, but since car A catches up to it, it travels that additional 200 meters. So we write plus 200. Now, if we're being specific, we could say, if we're like defining our variables, we could say dB is equal to dB. And the time that this takes is equal to TA and TB. They're using the same amount of time to do this motion. So we could just write T in our equations and not worry about, oh, it's not two different times, it's the same. And this is useful because we can solve for T in our V is equal to D over T equation. You cross multiply, you get D is equal to V times T, and we have an equation, T is equal to D over V. And we could write like this, and like that for car B, but since the times are the same, we can just set these two equations equal to each other. So that's where we'll start. Now, to continue doing the guess method, the next step is to substitute in our values. So for dA, we wrote an equation dB plus 200 over VA we know is 20 meters per second. We don't know what dB is, but VB is 15 meters per second. And now we have one equation with one unknown, and we can solve for dB. So you can cross multiply and then distribute the 15. And I made a transposition error here. It's 200, so it would be 15 dB plus 3,000 is equal to 20 dB. So then you get 5 dB is equal to 3,000, and you get the distance that B is traveling is 600 meters. But the question says, how far must A travel? So we use that equation that we made before, substitute in, and dA is equal to 800 meters, which is the answer. Now, there's a different way to look at this if we think about relative velocity. Relative velocity is the vector difference between the velocities of two bodies. The velocity of a body with respect to another regarded as being at rest. With all these problems, we've been using Earth as that second body, or our frame of reference. Typically, unless stated otherwise, we do use Earth as the frame of reference. But if we look at these other examples, for example, a tanker plane refueling a fighter jet. If you didn't know that they were moving with respect to the Earth, it looks like they're stationary with respect to each other. But they're going super fast. The tanker plane, their velocity relative to the Earth is 345 miles per hour east. The receiver plane's velocity relative to Earth is 345 miles per hour east. But the tanker plane's velocity relative to the receiver plane is 0 miles per hour. So it's the vector difference between the two velocities. Since it's the difference, you could just subtract them and you get 0 miles per hour. A little bit different example is a train. So if you've ever been on a train before and you're looking out the window, have you thought about relative velocity? See these trees moving? Are the trees the things that are moving, or is the train moving? If you took away all your prior experience of being a human being and maybe even being on a train, and you were looking at this picture, doesn't it look like the trees are the things that are moving and everything inside the train is stationary? Well, it depends on what your frame of reference is. So the tree velocity relative to Earth is 0 miles per hour. The trees aren't walking around. The train velocity relative to Earth is 40 miles per hour east. But what does that make? So let's say you're moving east on this train. If you're looking out the window and you consider yourself as stationary, then the trees must be moving backwards. The tree velocity relative to the train is 40 miles per hour west. So that's a little taste of what relative velocity is all about, and we can use it to help solve this problem. So in our example, it looks like that. Car A travels and it catches up to car B. But if we think of the relative velocity, if you were in car B, then everything else seems stationary to you, and the car A is traveling, it's catching up to you at a rate of 5 meters per second. You do 20 minus 15 to get that 5 meters per second. So this is what the equation looks like. It's the vector difference. So we could plug in. And now we can use this as a piece of given information. 5 meters per second is the relative velocity of car A to car B. Now, car A needs to travel a distance of 200 meters at this relative rate of speed, rate of change of displacement. So all we need to do now is find the time that it takes for this to happen. Then we can use that time and car A's velocity relative to Earth to solve for how far car A travels. So we'll set up our equation. This is the velocity of A to B and the distance that A travels relative to B. So we have 5 meters per second is equal to 200 over t. Then you get t is equal to 40 seconds. And now we're ready to finish the problem. Let's look at Earth's frame of reference again. The velocity of A, the distance that A travels relative to the Earth, and now we know the time. A is traveling at 20 meters per second relative to Earth. We're looking for how far it goes, but we know that this motion takes 40 seconds to complete. You cross multiply and you get the same answer, 800 meters. So that's two different ways to do the same kind of tricky problem. You have to use some critical thinking. That's about it. Thanks for watching. Have a great day.